Hello everybody. So we start with the lecture, our lecture number 5, and it will be about Liouville's formula. So this will be the final result of our lecture. Liouville's formula. Sit down, please. Hello. Okay, I'd like to recall some important points from the preceding lecture. So we have discussed, so we start to discuss vector differential equations of the form A of t is a matrix. A of t is a matrix n by n matrix times x. This is a linear homogeneous differential equation. And we're discussing the solutions of this equation. So we will discuss the general solution of this equation, and sometimes we will need the initial value problem. So for the initial value problem, we need some simultaneous, initial condition, right? X of t0 equals x0. This is the initial value problem, and this is a linear homogeneous differential equation. And we have proved theorem that the set of solutions of this linear homogeneous equation is a vector space of dimension n. So it was proved during the preceding lecture. So I'd like to recall this theorem. We will refer to it. So a set of solutions of, let it be equation number 1, is a vector space of dimension. Hello? Just wait. Please wait for a while. Of dimension n. Okay. Sit down, please. Take the place. Do you need... Just a moment. This is for you. Так, держите. Так. Так, ну тут вот два варианта. Вот один какой-нибудь оторвите, может, еще кто-нибудь придет. Right. Sorry for this. So it was proved, and now we continue our study of linear homogeneous equations, and we will discuss fundamental solutions. Okay, so I will give a definition. Right, it will be related to this theorem. Okay, so I'd like to introduce the notion of a fundamental solution. It will be a matrix. So an n by n matrix. Matrix x of t, whose columns form a basis of this set vector space of solutions, will be called a fundamental matrix. So an n by n matrix whose columns form a basis of the space of solutions. Hello. the space of solutions of one of the equation 1 is called a fundamental matrix. Fundamental solution, not matrix, but fundamental solution. Fundamental solution. It is not uniquely defined. It can be changed. We can change the basis in the space of solutions, and so we can choose this fundamental matrix in different ways, but all the matrices are related by some. So there is a relationship between two different bases, different fundamental solutions, and we will discuss it later. First of all, so I'd like to study properties of a fundamental solution, and I will study with this fact. So let it be lemma. It is trivial, but I will state it. If we take the derivative of this fundamental solution, of this matrix, then the derivative, which is calculated entry by entry, so we must differentiate each entry of this matrix, and this derivative will satisfy the following matrix equation. Okay, now let's try to check this. Okay, so x of t is formed by vectors, by the solutions of this set of solutions. So it is convenient to write it as, so maybe it will be, so to clarify, I will do the following. I will consider a matrix x1, 2 of t. I will write it as a matrix to explain the pattern. So x2, 2 of t, and so on, x2 n of t, dot, 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 x and 1 of t, x and 2 of t, x and n of t. So this is the matrix, the fundamental matrix, and by definition, the columns of this matrix are solutions to the equation 1, and they form a basis of the solution space. So let it be x1 bar. So this is the vector. I will call it x1, x2, the vector x2 of t, of course. They depend on t, xn of t. And I can rewrite this matrix as x1 of t, x2 of t, xn of t. Okay, what will happen when we multiply a matrix A of t by the matrix x of t? Let's do this. A of t multiplied by x of t. Okay, so we must, let it be A11, A1n, AN1, ANN. And we multiply this matrix by the vectors what shall we do to multiply this matrix by this matrix? We should take rows from this matrix, right, and multiply rows by columns. So, for example, if we fix this column and multiply this column by all of these rows, so we will get the first column of the new matrix. Okay. And since x1 is a solution of the equation, I will rewrite it on the differential equation, this one. So since x1 satisfies this equation, we can see that x1 prime equals a of t times x1 of t. And so we can see that the column x1 is multiplied by each row of the matrix A, and so as the first column we will get x1 prime of t. It follows from this equation, if we rewrite it in the reverse order, we will get exactly the equality that the equality that says that if we multiply the matrix A of t by the column vector x1, we will get the first column of this first column, right? So as the result of this multiplication, we will get the matrix consisting of the derivatives of solutions as columns. So we can see that this is the derivative of the fundamental matrix, and this is the fundamental matrix. And so this is just what we need. So the product of A of t and the matrix X of t will give us the derivative of the fundamental matrix. So proved. So this lemma is proved. Okay. Lemma 2, we can see that if we multiply the fundamental matrix by some vector c, so let's multiply x of t by the vector c. This means that we multiply the matrix by the column vector. What will be the result of this multiplication? What is the dimension? What is the size of the resulting matrix? Do you know the size of the resulting matrix? This is an n by n matrix, and we multiply it by the by n. So n. Right. Right, and n by 1, and the resulting matrix will be n by 1 matrix, of course, yes. So it will be x of t, some vector x of t. And I state that this vector is a solution. So if we consider a fundamental matrix and multiply the matrix by some vector c on the right, we will get a solution.
So c is a constant.
Right. C1 and so on, Cn are constants. And this will be the solution. Okay, why?
So it's going to be part of lemma 1. It corresponds to lemma 1.
Maybe, yes. So, but we multiply. So not exactly. So the difference is that we multiply by c on the right, and we multiply by the matrix A of t on the left. So they are different things. But to prove this, we can see that this product is the linear combination of column vectors of this matrix with these coefficients. So by definition of the matrix product. Sorry?
Because if you multiply n by n matrix, you multiply by n by 1 matrix, you get n by 1 matrix.
N by 1 matrix, yes, but we will use the rule of multiplication, right? So we need to. So if we want to multiply two matrices, we must multiply rows by columns, and we can see that. So the proof will be the following. It is elementary. So if x of t is rewritten as the column vectors, then multiplication of x1 of t dot x n of t by the vectors c1 and so on cn is just the linear combination of these vectors, right? c1 x1 of t plus dot plus cn xn of t, and we know that the vectors x1 and so on xn form the basis in the solution space, and so the linear combination will give us a solution, right? And conversely, if we consider any solution of our linear equation 1, then since we have proved that the set of solutions is a vector space of dimension n, so and our fundamental matrix is generated by the basis vectors as columns, so any solution is a linear combination of our basis vectors, and it can be represented as the product, the fundamental matrix by some constant constant vector c. So this is the form of any solution. Any solution can be represented in this form. Well, and now let's move further. Now we will need the following. So now I will prove the following important fact. Now we need to discuss linear dependence or independence of vectors. So it is important, linear dependence and independence of vectors. Maybe I will use that part of the blackboard. So linear dependence and independence. Of vectors. Okay. I'd like to recall something from linear algebra first, and then from the first part of the course of differential equations. So from linear algebra, so in the course of linear algebra, we can see the we can see the vectors, constant vectors, right? So v1 dot vn are some constant vectors. The components of these vectors do not depend on t; they are constants, right? And we have discussed linear dependence and independence of these vectors. So they are linearly dependent if there exist constants that are not all zero, right? Some of them must be non-zero, not all zero, such that the linear combination c1 v1 plus dot plus cn vn is a zero vector, linearly dependent And if this is not the case, or otherwise, if there are no such constants, then these vectors are called linearly independent. So linearly independent if this equation, so this equality, implies that all the coefficients are zero, linearly independent. So in the course of differential equations, our vectors may depend on t. So they depend on t. And we want to give the same definition, but I'd like to ask you, what about, for example, let's consider an example. Let's consider two vectors, one t and let it be v1, and v2, which is equal to 1 sine t. Are they linearly dependent or independent? What is your opinion? Independent, but if t is equal to 0, then they are equal. v1 is the same as v2, and they are equal to the same vector. So this means that at t equals 0, they are linearly dependent. Okay, so if we fix t, for example, t equals 0, then these vectors are linearly dependent. But generally, if we want to study linear dependence or independence on some interval, so if t belongs to is in some interval a, b, then they are linearly independent. They are linearly independent. Since, so if we consider the same equation, it will be c1 times v1 plus c2 v2 equals 0. So this equation must be satisfied for any value of t. So c1 and c2 must be constant. They should not depend on t, right? They should be constant. And if this equation is satisfied for any t and for non-zero constants, then these vectors are linearly dependent. And if this equation, which is satisfied for any t and constant and fixed constants, if this equation implies c1 equals c2 equals 0, then these vectors are linearly independent. Okay. All right. And so this example shows that sometimes, so it is possible for two vectors to be linearly independent generally, but they are linearly dependent at some point, a fixed point, right? So they are linearly independent on the interval, and they are linearly dependent for some value of t. And now I'd like to state and prove some very important theorem. It states that this situation is not possible for solutions of the linear differential equation. Okay, so it will be so theorem number 1 for today. Okay, so if x of t is a fundamental solution, then so its columns are linearly independent for any t. Any t so this is important. There can't be t for which they're linearly dependent. So these two vectors can't be can't form the basis in the solution space for some linear differential equation. So there is no linear differential equation of that form for which these two vectors form the basis, because they are linearly dependent for one value of t. So for
Then it's called columns, right?
columns, right? Columns. Columns. Its columns are linearly independent. Okay. So now let's prove this theorem. Okay, suppose x of t is a fundamental solution. Is a fundamental solution of 1. Let's take any value of t0. Let's fix t0. Now let's consider some linear combination of the columns. So suppose x1 of t and xn of t are columns of this matrix. So I need to introduce the columns, the vectors x1 and so on xn. We know that they are solutions of 1. They satisfy 1 and they form the basis in the solution space. So take any value of t and consider a linear combination. Cn xn of t0. Suppose this linear combination is 0. And I'd like to prove that this implies that C1 and Cn are all 0. Let's prove this. Let's try to prove this. Okay. Well, so let's consider an initial value problem. X prime equals a of t times x, and x of t0 equals x0. Equals not x0, but equals 0. The 0 vector. First, I claim that the zero solution will satisfy this initial value problem. So if we consider a solution x of t equals a 0 vector identically 0, right, for any value of t, then this solution satisfies this initial value problem. Let's check this. So this initial condition is satisfied. And what about this? So if we multiply a of t by a 0 vector, we will get a 0 vector, right? And the derivative of a 0 vector is 0. So this solution satisfies our equation and initial condition. So this is a solution of this initial value problem. On the other hand, if x1 and so on xn are solutions, then their linear combination is a solution. So from on the other hand, so the function x of t, which is a linear combination of our vectors, is a solution. Why? Because x1 and so on xn are solutions, then their linear combination is a solution. Right. What about this condition, this initial condition? So we know that this linear combination at the point t0 is equal to 0. So the initial condition is also satisfied. So we can see that this function satisfies initial value problem. So there are two solutions for the initial value problem. But we know from Picard-Lindelof theorem, we know that the solution is unique. So this means that this is identical 0, right? So this linear combination is equal to 0 identically, because this solution must coincide with this solution, right? So this must be a 0 vector. So right. So this is identical 0. So but we know that x1 and so on xn form the basis in the solution space. So we know that this is identical 0, but since they form the basis, it follows that c1 equals cn 0, right? So if I'd like to maybe to recall some important points from this proof. So the first step, right, we consider fundamental solution, right, a fundamental matrix. We take any point to t0, and we want to prove that if this linear combination is equal to 0 at the point t0, then all the coefficients are identical 0. Why? So next we use the Picard-Lindelof theorem of existence and uniqueness of the solution of the initial value problem. And we can see that these two solutions are the same, and so we can derive from this fact. From this fact, we can derive that this is 0 not only at the point t0, but at any real t, right? It is identical 0 for any t. And so this implies that all the constants are 0. So this is the logic of our proof. So it is completed. And now, okay, so we will speak about the Wronskian. I hope you remember something from the preceding semester, right? So the Wronskian. The Wronskian of the vector functions. The vector functions x1 of t dot xn of t. They must be n-dimensional vectors, and the number of these vectors is n. So the Wronskian is the determinant of the matrix formed by these vectors as columns. And it is denoted by W of t, or sometimes we will write like this. So it is the determinant of the matrix x1 of t, xn of t. The determinant of the matrix generated by these vectors as columns. This is the Wronskian. And we may obtain the corollary from our theorem 1. So if x1 of t dot xn of t are solutions of the differential equation 1, then either W of x1 xn t is not 0 for any t, any real t, or W of x1 xn t is identically 0 for any value of t. It is not possible for the Wronskian to be equal to 0 for some values of t and to be non-zero for other values of t. So it is it can be equal to 0 for any value of t, or it is identically 0 for all values of t. So there are two alternatives only. Okay, so this is the important corollary. Next, now I'd like to prove some fact about the solution to the initial value problem. So now let's describe the solution of the initial value problem in terms of a fundamental matrix. Theorem number 2. If x of t is a fundamental matrix, is a fundamental solution, of 1, then the solution of the initial value problem is given by the following formula: x of t, so x, the vector x, is equal to x of t times x of t0 inverse times the vector x0. So using the fundamental, the problem is, suppose we know a fundamental matrix. So it is not uniquely defined. There are different fundamental matrices. So by the way, they are related by the formula. If x of t and y of t are two fundamental matrix. So this is the remark. If x of t and y of t are two different fundamental matrices, fundamental solutions, maybe it's better. Solutions. Then they are related by some matrix, some invertible matrix, non-degenerate matrix C. So where C is a matrix, not a vector, a matrix. So they are related by this formula. Well, so this is a remark. This is a remark. But now, so suppose we know some fundamental solution. We are given this value t0, and we are given this initial vector, right? So this is the answer how to find the solution to the initial value problem. So if we have a initial value problem, so we need a particular solution satisfying these initial conditions, right? Okay, so the proof is elementary. So first, let's prove that x of t given by this formula satisfy this differential equation. Satisfies differential equation 1. So it was already proved, has been already proved, because this is a constant, this is some constant vector. A matrix n by n matrix is multiplied by n by 1 matrix. So this is a vector. We may call it C. And we know, we have already seen that if we multiply a fundamental solution by some constant matrix C on the right, we will get a solution to the differential equation. So it satisfies 1. And step number 2, we must prove that it satisfies the initial conditions. So let's consider, let's compute x of t0. Let's substitute t0 for t, and we will get the product of the fundamental solution times x of t0 inverse. And this will give us the identity matrix, right? And times x0. So the result will be identity matrix multiplied by x0, and it is x0, the vector x0. So proved. Very easy. Right? Okay. What about the break? I think we will finish the lecture. Right. So now we will prove some. So the last very important theorem, it is called Louisville's formula. So this is the name of our lecture, and the title of our lecture, Louisville's formula. Right? We will prove it now, and after this we will have a break before the seminar. Let's state and prove Louisville's formula.
Seminar also consists of application of formula.
So the Louisville's formula has an application, but I think we will discuss it later. Today, during this seminar, we will discuss Wronskians and some effects related to the Wronskians. And after this, we will discuss seminar number 2, so problems from homework number 2. This is the plan for the seminars, but we will apply, of course, we will apply the Louisville's formula to find the solutions of the differential equations. Now, let's state and prove Louisville's formula. Okay, theorem 3. Okay, if x of t is a fundamental solution of the equation of this equation, then if we fix t0 for any t0, the Wronskians of x of t is equal to the Wronskian of x of t0 if we fix, so suppose we fix t0 and let t vary, then the Wronskian calculated at some time t is equal to the Wronskian computed at t0 multiplied by the exponent of the integral from t0 to t, the trace of the matrix. I will recall what it is, a of s ds. The exponent means e raised to the power integral from t0 to t trace a of s ds. This is the same. The exponent.
Is it like moving? Like, is this
proof will be algebraic. But yes, maybe if we fix point t0, so if we fix t0 and if we compute the Wronskian of this fundamental solution at the point t0, and if then we move to the point t, then the new Wronskian will be equal to the product of the old Wronskian, original Wronskian computed calculated at the point t0 times the exponent of this integral, right? So for any t and t0 from R. Now we will prove it. So first of all, now I'd like to obtain the differential equation for finding Wronskian. So the Wronskian will satisfy some differential equation. I'd like to obtain this differential equation. So obtain a differential equation to which the Wronskian satisfies. So for Wronskian, f of x of t. So suppose x of t is a fundamental solution. I will write it x11, x12, dot, 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 x1n. Sometimes we will use this matrix xn1, xn2, xnn. So they all the entries depend on t. We will call them x1, x2, and so on, xn. And I want to find the derivative of the Wronskian. So we obtain the determinant of this matrix, and then we will try to differentiate it, right? So the derivative of the Wronskian. I'd like to obtain the formula in terms of the matrix A, right, the Wronskian W of x, in terms of the matrix A, exactly, in terms of the matrix A. Okay, so let's try to differentiate the determinant of this matrix. How to do this? To differentiate the determinant. Right, so let's try to do this. Maybe we will try with 2 by 2 matrix if you want.
Yeah.
Let's try 2 by 2 matrix. X, Y, 1, 1, or let it be A, B, C, D. Suppose all the entries depend on T, and let's try to first find the determinant. It is equal to AD minus BC, and then try to differentiate it. It will be A prime D plus AD prime minus B prime C minus BC prime using the product rule. Next, we can group them as A prime D minus B prime C plus AD prime minus BC prime, and I'd like to rewrite it as the sum of the determinants. So look at the first term. It is the determinant of the matrix A prime, B prime, C, and D. So plus the determinant of the matrix A, B, C prime, D prime. The sum of these two determinants. Right? Can you see this? Can you guess what happens with the determinant of 3 by 3 matrix? What is your opinion if we try to differentiate 3 by 3 matrix? Just a moment. X2, 3. I may do it. So I may do it explicitly, right? But maybe we try to guess. What is the result? So the derivative of this determinant, what will be the result?
Differentiation of first row plus.
Right. So we will differentiate the first row. And we will rewrite other rows. We will leave other rows unchanged, right? X2, 3, X3, 1, X3, 2, X3, 3, right? Plus what? Next, we need to differentiate the second row. The second row. This will follow from the product rule, because so just think about this determinant. So each term of this determinant is the product of 3 values. For example, x11 times x22 times x33. And if we apply the product rule to the product of these 3 functions, then we will get, so I will use this space. So if we differentiate, for example, x11, x22, x33, the product will be x11 prime x22, x33 plus x11, x22 prime you can see 3 terms. The first will come from this matrix, right? Next, we need to differentiate the second row. And plus the determinant of the matrix in which we differentiate the third row. So these 3 terms give rise to these 3 determinants. So the sum of 3 determinants. And now what about the general case? Let's try to guess. In general case, what is the formula for the determinant of the derivative of the determinant? The sum of n matrices, let's call it, they D1, D2, and so on. So it will be D1 plus d2 plus dot dn. Okay, where di is the determinant of the matrix formed by the determinant of the matrix which coincide with the original matrix except for the ith row. So we take the derivative of the row number I of this matrix, and we leave the other entries unchanged, the same, right? And so we will call it di. So in the ith row we must write the derivatives, take the derivatives of the entries, right? xi2 prime dot xin prime. And the other rows are the same as the rows of the original matrix x of t. Okay, is it clear? Right. So this fact can be generalized.
Again, so the di is basically only the row, right?
Not only the row, the determinant of this matrix. So we should take this matrix. Yes. We should differentiate one row. So fix row number I, differentiate this row, and leave the other rows unchanged, and form the new determinant, the determinant of this matrix.
What I meant is like D1 is only one row determinant, right?
One row determinant, right? Right. Correct. Right. Difficult to explain. Right. Now we will use. I'd like to include so my goal is to obtain the expression of this determinant in terms of the matrix A. So I must use this equation. So we know the formula for the derivatives of xi's. They are given by this formula, right? So let's consider di for some fixed I. Let's consider the ith row number I. What can we say about this row? xi1 dot xin. So we know this formula. And to obtain this row, ith row, we must multiply so the matrix and times the this vector, or so we will use this. We know that x of t, the fundamental solution, is equal to the product a of t times x of t. We know this, and it's better to use this, I think. Right. To obtain this row, we must fix the row of the matrix A, ith row, and multiply by the columns, by these columns. Right. So I mean that xij, for example, prime, is equal to, by the definition of the product of matrices, it is equal to the sum a I k runs from 1 to n times x k j. Right? If we fix I and j varies from 1 to n, then we can see that this is the linear combination of columns of this matrix with the coefficients taken from the ith row of A, right? So we can see that it is A I1 times one, just a moment. let it be, I will rewrite it as the sum A I K, and this will be X K vary from 1 to and this should be done for any K, right? Just a moment. Must be I think it should be like something like this. 1 1 1. Not it must be X2 1. Just a moment. I will write it as the product. It's better. It must be, so we must fix the row I1 I2 dot 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 AIN. And multiply it by columns of X of T. I will rewrite. Maybe it's better to rewrite it. X11, X12, X1n. Right. Maybe just a moment. X and n and 1 and 2 and n. Okay. So next we multiply columns by this row. Right, row number I, and so we can see that all the entries from the first row are multiplied by AI1. Right, all the entries from the second row are multiplied by AI2. So we can see that this is the linear combination. So using in terms of the rows of the matrix xt, we can see that we must find the linear combination of these rows with these coefficients. Right? So we must multiply the first row by AI1, add AI2 multiplied by the second row, and plus AIN multiplied by xn1 and so on, xnn. So we can see that this row is the linear combination of these rows with these coefficients. Right? Can you see this? Okay, so to multiply the matrix by this row, we should multiply columns by rows, right? So AI1 is multiplied by x11, then by x12, and so on. You can see that all the entries of these rows are multiplied by AI1, right? So it is written here. Next, we must add, right? Because we find the sums. Then we multiply the second row by I2. This is I2. So we can see that this row is a linear combination of the rows of this matrix. Now, what about the determinant? Let's turn to the determinant. We need to find the determinant di. So we have the rows x11 dot 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 x1n. x to 1 to n. Okay, and the ith row, row number I, is replaced by this linear combination of the rows of this matrix.
So this is what we've done from there.
Right, so this must be placed here. And the last row will be x and 1 dot 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 x and n. What is the what is about the determinant? Can you use some properties of the determinant to find the determinant of this matrix? So if we multiply some row by some constant and add to another row, what will be the result? What will be the how the determinant will change? So it is unchanged, of course. Yes, it will be unchanged except for the ith row. So you can see that ith row is multiplied by ai, right? So the first row is multiplied by ai1 and added to this row, and this will leave the determinant unchanged, right? If we multiply the second row by, so this row is multiplied by I1, this row is multiplied by ai2, and so on, but the original row is multiplied by aii. And so this will give us the coefficient aii. So I state that this is equal to aii times the Wronskian. Is it clear? Because we know that the determinant of the original matrix is the Wronskian. Next, and if we then if we replace row number I by the linear combination of the rows of this matrix with these coefficients, that will not change the matrix except for the original row, which is multiplied by aii. So this coefficient should be moved out of the determinant, and so this will give us this multiplication, right? Okay, so we know that the derivative of the Wronskian is equal to the sum of di's, I runs from 1 to n, then each determinant is equal to, can be replaced by aii times v of t. Oh, let it be v of t, from 1 to n. So this is the common factor, and we can so what is the sum? So this is the sum of the diagonal, the entries of the main diagonal. This is just the trace of the matrix, the trace of the matrix. Trace, what is the trace? Trace is the sum of the entries of the main diagonal. This is the trace. So this is trace of a of t times v of t. So we have obtained the differential equation for finding the Wronskian. So A is a given matrix and Wronskian is the unknown function, and we can find the Wronskian from this differential equation. We can just solve the differential equation. It is not a vector equation, it is a scale equation, because this is a number, this is the scalar function depending on t, and the trace is the function depending on t also. So let's solve this differential equation. This is step number 2, to solve this differential equation.
Oh, this is step number 1?
All right, this was step number 1, to differentiate the Wronskian. This was step number 1. Yes, and step number 2 is very easy. So we just solve this differential equation. We know the algorithm how to solve linear differential equation. Just so the variables are separated. The variables are separated. Step number 2, solve this. The derivative of the Wronskian is equal to trace a of t times the Wronskian. Let's solve it. So the variables are separated, and so we can easily solve it. I have separated the variables. what shall we do then after this? So integrate both parts. Okay, so we have the logarithm of the Wronskian. Okay, we can divide by the Wronskian because it is never zero by the preceding theorem. It was proved in the preceding theorem. So the logarithm of the Wronskian is equal to okay, so the integral, right? I will leave it. A of trace of the matrix A of t dt. Okay, and maybe plus the constant, and from here we can find that the if we use the exponent, then the Wronskian is equal to c times so since it depends on t, I will use another argument s, trace A of s. I will change the so the variable of integration. This is the integral. And now if we use the initial condition, how to find c, right? So we know that at t so we know the Wronskian w of t0, and using this initial condition we can find that w of t equals, so c can be easily found, it is w of t0 times the exponent of this function. Okay, how to find c? So suppose we know that at the point t0 the Wronskian is w of t0. Okay, so substitute t0 to both parts of this, so and c can be easily found, and so the integral will be from t0 to t. So I think it's better to include them so to consider not the indefinite integral, but it's better to consider definite integral, right? So it must depend on t, so the integral from t0 to t. So this is the function depending on t, so we must use the definite integral. So formula is proved. That's all.